Vediamo.
Ciao.
Questo è uno. Devo caricare anche l'altro.
Sì, più che altro mi chiedono per seguire meglio quello che è in corso.
Ok.
Benissimo, grazie. Allora, a questo punto ti colleghi il tuo schermo.
Oh, no.
Because maybe I have my own one.
Marco, però non mi date tempo, non so come ho fatto a la cosa sul
Sì, a metà e quanto prima della fine. Prova a toccare qualcosa.
Zoom siamo ancora collegati? Mai detto come ho fatto prima con Zoom? Ah, mi hai mandato un link.
Mandate il link su WhatsApp.
Un segnale.
Chiudi il tuo audio. Però non abbiamo il tuo video schermo. Prova a staccare e rientrare. Ok. A questo punto condividi il desktop e lo fai partire. Sì.
Vediamo se funziona.
So we are going to start. You can find on the Indico website the slides of the previous and of the current presentation by Giuliana. So we will go.
Okay. If I understand correctly, the previous lecture was too dense. Sorry. This one will be sorry, so you can relax. No notes to take. The slides are already there. You can take a nice sleep. Okay. So. Okay. So, second part, we start from where we left, that is dark matter detectors for with novel liquids. And then I will try to give this small overview of neutrino detectors. Okay, so you have already seen this graph shown by Marco this morning, the huge range of possible candidates for that matter. We don't know what it is. We cannot use a single technology to address this problem. And actually, there has been a change of paradigm during the last few years from a period in which we were only looking for WIMPs because we were really convinced that they were miracle solving problems both in the practical physics and astrophysics and cosmology, and so they should be there. I remember my thoughts at that time were, it is there and we will find it. Of course, now the attitude must be different because we have serious doubts. that winds are there. Nevertheless, we have not covered the full range of parameters that is foreseen, predicted by the supersymmetric models and other models. As you heard this morning, winds are a very broad class of candidates. And the predictions for winds are in a region which is not fully investigated yet. So large enterprises, which costed a lot of money, a lot of efforts to many of us, are still ongoing. And this will be one big part of my presentation. Of course, like that matter, as you said this morning, as you heard this morning, is gaining a lot of interest, attracting a lot of efforts from many different communities, but also from our community. That is, the community that developed the novel liquid detectors to search for winds is also putting some effort, quite a lot of effort, in looking for LiDAR mappers. So the spectrum of candidates that I will cover is quite large, going from below the TeV to the hundreds of TeV, while the ultralight dark matter really needs different kinds of technical approaches, and I think will be covered in another lecture. Okay, so let's go back to the wind paradigm, just to cover that part that was not covered by Marco this morning. How to look for actively for these candidates, not looking at the possible annihilations or productions in the galaxy or from extragalactic sources, but for direct detection, for what is needed to demonstrate the existence of a particle candidate. You already know the features of these candidates, so I will jump to the technique. The technique was illustrated. I always use this picture because I liked it a lot. It's from a paper appeared in Nature in 2009, just to give you the idea of when, what is the time period in which these efforts that I'm going to describe were actually designed and thought of. The idea is that we are immersed in a halo of wind particles, weakly interactive massive particles, whatever they are. As Marco explained and underlined many times this morning, these candidates have very general features that are common to all possible candidates. And these are essentially that they are thermalized inside the halo. We can even measure the distribution of these candidates of these particles in the halo, galactic halo. And this means that we, with our detector on the Earth, are together with the sun, which is moving in the galaxy, we are traveling in this halo of particles, seeing a wind impinging on us as if we were walking in the rain, and you see the rain coming towards you because of the relative motion between you and the rain. Exactly in the same way, our sun travels in the galaxy and sees a wind of dark matter particles. As we, with our terrestrial detector, are moving around the sun, not only we see this wind, but we see it modulating with the rotation of the Earth, the revolution of the Earth around the sun, which for half of the year is in opposition with the velocity of the sun with respect to the galactic halo, and for the other half of the year it's in phase with that motion. So we see a flux of winds which is modulating, increasing, and then decreasing with a period of 1 year. And this is essentially one of the signatures of the signal that you would expect on your detector. What is the signal? Well, the signal is very simple. If the winds have any kind of interaction with normal matter, they will possibly have a scatter against no terrestrial target, And the flux, the rate of these interactions will be given essentially by the incoming flux, which is the density, the number density multiplied by the average velocity. Of course, everything must be averaged with the cross-section of the interaction. So the ingredients to evaluate the magnitude of this rate of event in your detector is predictable if you know the density of the numerical density of the particles in the halo. So essentially the density that was given by Marco this morning divided by the mass of the particle that you are considering. Multiplied by the number of targets in your detector, and multiplied by the velocity, the relative velocity of your terrestrial detector with respect to the halo. And the other ingredient is the cross-section of the scattering. The first two elements come from astrophysics, and you have already seen these two distributions this morning. There were different pictures, but exactly the same numbers. The density at the terrestrial spot in the galaxy should be around, I would say, is that the density? Yes, 0.3 GeV per cubic centimeter. You will say 0.4, it's between 0.3 and 0.35. And the velocity is given by 230 kilometers per second. So you have these two ingredients from astrophysics, and it's more or less independent from the mass candidate, the candidate mass that you are considering. The cross section is your unknown. You want to measure it in theory, so you don't know, and you explore possible regions of how much is this of the value of this cross section by looking for the scattering on nucleons. The scattering on nucleon is a non-relativistic scattering because the velocity are 1/1000th of the velocity of light. The flux with this velocity is can be calculated for any mass that you hypothesize. For instance, for 100 GeV, is of the order of 10 to the 5 per second per square centimeter. So there are quite a lot of these WIMPs that are impinging on our target. And once you put in the kinematics and the distribution of the dark matter in the halo, which is more or less Maxwellian, you find that the expected rate is exponentially falling, which is a very bad news because everything is exponentially falling. Whatever you are measuring, whatever kind of physics you are doing, you will find that it is exponential somewhere. So it's not very peculiar, and it's not a good way to detect candidates of something because they will be similar to anything else. Normal radioactivity in your detector will also produce exponentially falling rates. So that's a bad news. On the other hand, this is a very simplistic approximation. You have factors here that depends on the particle physics, which is inside the interaction rate, which take into account, first of all, of course, this possible modulation of the signal, which is due to the galactic motion, to the galactic origin of the signal, and that's one possibility. Another interesting feature comes from the fact that whatever the interaction is, as it is non-relativistic and with low energies involved, it will involve coherently the nucleus with which you are scattering, not the single nucleon, but the nuclei. And so there will be a form factor given by the kind of interaction that you are considering, and the form factor in some way helps you because it gives you information on what exactly is interacting with what. See here, for instance, these form factors, the effect of these form factors on the expected rate. So here you have the expected rate expressed in events per ton per kV per year, events per ton per year. Okay, so really rare events for different targets with respect to the recoil energy of the nucleus, which is interacting. And you see that there is, of course, the effect of coherence of the scattering, which goes more or less with A square, generally speaking. And this means that heavy target nuclei will be favored because they will, you will have a higher number of events going with A square. On the other end, these events will be mostly at low energy of recoil, so many but difficult to detect because the lower the energy, the more difficult it is. While lighter nuclei, target nuclei, are enhanced in the probability, in particular for these golden type high energy events, by the form factors. So this deflation here is due to the form factor of heavy nuclei, which favors instead lighter nuclei. So at the end, you can choose your target according to what kind of candidate you want to investigate, or better, you can use many targets with different different mass, so that you can exploit both these characteristics. The fact that at low energy events, you will have an enhancement of the cross-section due to the coherence of the cross-section, while for the easier high energy events, you will use lighter targets. So better to use many targets in order to exploit these, which is one of the few features of this scattering. The numbers that I give here come from this simplified formula, which I have derived myself, I think 1,000 times. Every time I get a different number. Anyway, should be right this time, I hope. It's, as you see, expressed in natural units. And these natural units evolve in time and with my age. So when I was young, the natural units here were 10 to the minus 38 square centimeters, because that was the, at that time, currently investigated cross-section. And now that I'm old, we have a natural unit which is much lower than that, and very recent results, which I will show you, investigate cross-sections as low as 10 to the minus 48 square centimeters, for which, of course, you need many, many tons of target and many years of exposure. Okay, so one of the keywords of this presentation will be the exposure, which is the product of the mass of the target for times the time you use the target in the correct conditions to investigate and look for these bands. Okay, another plot which is very popular these days is this one, which shows you the kinematical limit of the energies you can investigate, of the masses, sorry, you can investigate when you have a detector that is sensitive to a given energy range. So as the scattering is not non-relativistic, it's very, very simple kinematics. You just have to know what is the energy that you are sensitive to. Just take into account the kinetic energy of your WIMP that can be given to your target, and at the end you need to detect that the kinetic energy. And you see that in order to investigate masses of the order of the MEB, so light WIMPs or light dark matter, you need to investigate energies of the order of the electron volt. So we are far from the range of energies which can be investigated with a particle detector. You have seen the ranges of energies for which we can detect a signal. So, of course, if you have a light target, that is, you investigate the interactions on electrons of the target instead of the nuclei, then this is kinematically advantageous. So if you want to have sensitivity to light dark matter, you will look for scattering on electrons. While if you want to be sensitive to heavier dark matter, you will look for scattering on nuclei. The equations and the rate calculations are very similar in the two cases. Of course, in the case of an electron, you need to take into account the fact that the electron is inside an atom and needs to receive enough energy to be kicked out of the atom. Okay. If you want to go to even lower masses, then you need to look for phonons, that is the collective motions inside your dense target, and the tools that I am describing here are not long useful, and they will be described in another lecture. So finally, the sensitivity of an experiment is expressed by this very, we call it vanilla plot. That means simplified view of the interaction. The interaction might be any kind. So it's very popular to examine the possibilities of the scattering of the WIMP on your target in an effective field theory. That is, you examine every possible coupling to your candidate, scalar, pseudoscalar, vectorial, tensorial, whatever, and you exclude all the possible candidates or try to investigate each of them. But in the simplest case of a scalar interaction, which we call spin independent, you can express the results of your experiment in this plane, which is the interaction cross-section of the dark matter with your nucleus or electron. It depends on what you are looking at, versus the mass of the dark matter particles, which are the two ingredients two unknown in the formula that I showed before. So if you look for scattering on nuclei, as I said, you are sensitive in a region from GeV, more or less masses up to several hundred TeV. The maximal sensitivity here depends on the exposure. So how big your detector, how long you expose it. So the larger, the more sensitive it will be, and the smaller cross-section you will be able to investigate. This rising edge here comes from the fact that you cannot investigate very low energy of recoils, so not very low masses particles that will release little energy. So this is the energy threshold effect of your detector. If your detector has a low energy threshold, then you will be sensitive to lower masses here. And this effect here is essentially derives with one of the mass of the particles, and it is given by the astrophysical characteristics of the velocity of the particle in the galaxy. So you cannot operate on them. As I said, now we are at the level of 10 to the minus 48 square centimeters, but we are pushing a lot in this region for higher cross sections by looking at electronic recoils, that is scatterings on electrons. This is done with a lot of problems from the experimental point of view, because the interaction is very simple that you are imagining. The physics involved is simplified because we don't know the details and we don't look at the details. We just try to look to whatever is scattering in your detector and in whatever way. The problem is that whatever is scattering in your detector, I mean, if you have neutrons or alpha particles around, they will scatter on nuclei and they will produce exactly the same recoil spectrum as a WIMP. And if you have gamma or electrons from beta decays or gamma decays, they will most probably interact with the electrons of your target and they will produce electron recoils. So how can you do that? How can you distinguish your good candidates from the overwhelming and huge background that you have in your detector? By reducing the background. Here is a sketch from the Xenon collaboration, which is, I think, very nice. It was published, if I'm not wrong, in their Darwin paper. You see that the spectrum that you expect from the WIMP is something like that. This is the spectrum as a function of the recoil energy. And your backgrounds go exactly in the same way. Here you have neutrons, which produce scattering. The only way to detect your signal is to keep the neutrons below that. So you have to reduce the number of neutrons in your detector. There's nothing else to do. The electron recoils will be huge with respect to the expected signal, but you can abate this background if you can tag them. So if you recognize that the electron recoils and discriminate versus the nuclear recoils, then they will not bother you. And finally, you have this line here, neutrinos, here and here. Neutrinos are the ultimate background because they will be there, coming from atmospheric cosmic rays, showers from cosmic rays, or from the solar production, as you heard yesterday, and they will, at least at the end, interact with your detector. And they can do either scattering on electrons, actually this is one of the ways in which we detect neutrinos, so they will, and they will also produce coherent scattering on nuclei, exactly like the WIMP Marco Pallavicini yesterday mentioned, this interesting physics that was for the first time observed very recently. This coherent scattering of neutrinos on your detector will produce a spectrum very, very similar, not identical, but very similar to the WIMPs. And so you will have to cope with it. On the other hand, Marco underlined that the energy of the recoils coming from these neutrinos, which are of the MEB energy, is very, very low. And this means that the recoils will have very low energy, and so they will be difficult to detect, and at the end their number will be low, fortunately. So what you do, you first of all go underground, of course, like you already do for neutrinos coming from the space, so that you abate the cosmic ray background, not from neutrinos, but normal cosmic ray background of several orders of magnitude, of the order of 6 or 7 orders of magnitude, by going, for instance, underground Sasso. And in addition, you use two techniques which were not so obvious many years ago. Actually, the first experiments did not use them, but nowadays are, of course, broadly used everywhere. That is, you use a Vito detector, first of all. So one thing that will distinguish the scattering coming from neutrons, for instance, or from WIMPs, is that neutrons have a high probability of scattering on your detector with respect to WIMPs. So if your detector is large enough, or if you have a good detector for neutrons, you can make these neutrons interact at least twice. At that point, you can exclude that it's a WIMP because the probability of an interaction will be squared 10 to the minus 38, 10 to the minus 45 squared. So very, very rare. And so it's impossible that a WIMP scatters twice. So detecting the double scattering was one of the first ideas that came up in order to discriminate neutrons from WIMPs. And this can be done either by putting around your detector another detector which has very, very high cross-section for neutrons, or using your own detector with featherization, using a fraction of the mass of your detector, which is a good detector, to tag neutrons, renounce to WIMP scattering there, but the remaining part of the detector, the inner core, will be golden, will be only there for WIMPs, because neutrons will have the probability of scattering twice. And this is true also for gammas. Gammas have the same probability of scattering twice with Compton scattering. Or, and this is newer, you use the electron recoil, nuclear recoil discrimination. With this, you can do nothing for neutrons, but you can do a lot for the remaining background. And we have already seen that this is done by exploiting the fact that the vast majority of detectors, in particular the noble liquids, provide you a redundancy in the measurement of the more signals, not only one signal. For instance, charge and light. And you normally charge and light, or whatever signals you are using, have a ratio which depends on the nature of the particle. Okay, so many different technologies are used more or less in the same way. In particular, the first experiments were using scintillation, and were using crystals to detect the scintillation light from WIMP scattering. Then we have started to look for ionization with bolometers. And then we have started to look at least at two channels, so detectors that could see both charge and light, like the noble liquid detectors, but also like other bolometers that can also look at heat, for instance, and light, or heat and charge. So all these experiments, which have a huge variety, are sensitive in different regions of the spectrum because of the different nature of the nuclei, target nuclei. So the complementarity of these experiments is one very interesting and rich feature of this kind of experiments. Of course, I will focus on noble liquids. So here is the picture, the global picture, current. We have excluded many orders of magnitude in the cross-section and in the mass with the previous experiments. And we are now investigating this region, as I said, around 10 to the minus 48 square centimeters. Unfortunately, very recently, late August, the latest results, as you will see, has covered down to 10 to the minus 48. I say unfortunately because there are planned experiments which are in construction that are sensitive in this region, which I'm building. So, of course, I'm not happy that somebody else arrives before me. Then there is a region where these experiments, either running or planned, will start to lose sensitivity because they will have to fight with this background coming from the neutrino, so-called fog. A fog of events where the possibility that they are coming from neutrinos cannot be excluded. This doesn't forbid you to make the experiment, because still you can exploit statistics, but the improvement in sensitivity will not scale anymore with the exposure in the same way. You will start to have background coming from neutrinos, and you will have to look for excess of events over this background. And currently, very big experiments, in particular with xenon, are just now facing this problem, starting to face this problem. This neutrino fog here comes from the atmospheric neutrino scattering, coherent scattering on nuclei that are in the MEV and 10 MEV region, and so they are comparable to WIMPs of the order of 100 GeV, while as you can see, this neutrino fog is much higher at lower energies because of the appearance of solar neutrinos, which are lower energies, and of course they have a higher probability of producing these events in your detector. So it is more difficult here. On the other hand, this is also the region where the noble liquids start to lose sensitivity. There is a region where the planned experiments are still sensitive. And then there is a huge space for new technologies. So many of us are now looking at this region here, either here or how to go deep into the neutrino fog. And that's, as I said, where the perspective should be. You are young, you should start thinking to this region. Okay? Either how to overcome the neutrino fog or how to go lower with masses. The technologies of the current experiments were already shown in my previous lecture. So I already explained these two kinds. I will show you something about the running experiments in single phase, which are essentially only T36 because X-mass, which was based on xenon, stopped its data taking and joined the xenon collaboration of TPCs. And these TPCs are now spearheading the scientific panorama with the best results. But I would like also to mention this, which is in the R&D phase. In this case, we use liquid helium, not liquid argon or liquid xenon. The physics is the same, but the cryogenics is much more complicated. You have to go to 4 Kelvin. So we are talking about small detectors at the moment. But this can scintillate like in the other detectors that I that I described, so you can detect the scintillation light in the same way. But in addition, given the very low temperature, you can exploit the the technologies which were in this plot here. Technologies developed to detect phonons, heat released by the particles. If you exploit these, in particular with superconductive sensors, you can, in addition to light, measure the phonons released by the interaction, that is heat, collective motion of the atoms inside. And you can even extract in the gas phase the helium, as we do in double phase, and then detect the single helium atom on a superconductive detector here. So this is really interesting. It's a new way to look to existing technologies. So noble liquids on one side with all the technologies developed for noble liquids, and superconductive devices on the other side with all the technologies developed for bolometers, and put them together into something that potentially could be a real breakthrough, because the threshold, the energy threshold of these phonon signals will be as small as 1 milli electron volt. So much, much lower than the keV threshold of our detectors. So this is something that I wanted to mention. It's in the R&D phase. Okay, let's give you an overview of the xenon detectors. It was very difficult for me to decide what to show, because I could imagine that there would be many people from xenon, and I wouldn't like to describe the xenon experiment to people who is doing xenon experiments. So I hope that there are posters, I think, at this conference, this school, from people working on xenon, and you can look at that. I opted for, as I said, a perspective view. So this slide is also quite used. There are several versions of this slide, which should show how the progress in the technology development for this xenon technology, starting in the early 2000s, let's say before 2010, with very small detectors of the size of a few kilograms, improved exponentially over the years, eating up decades of cross-section values per decade of time. So really impressive progress, which led from the initial Xenon 10 experiments, one of the first to have a high sensitivity for this kind of physics, together with the Zeppelin English British experiments, led first to Xenon 100, which really was a wonderful experiment and demonstrated the technology at levels which were not comparable to all the other experiments. Then led to the LUX experiment, 250 kilos. Then with the X mass, as I said, it reached the ton scale. And finally, with the Xenon 1 ton and n-ton experiments, overcome even that threshold, and now we are at several tens tons. There are, and that's an interesting fact, 3 families of these n-ton experiments. One is in Gran Sasso Laboratory, and it's the original, let's say, collaboration led by Elena Prila, which I already mentioned. Then another one was started in China by the husband of Elena, and it's a very similar experiment of the same size, competing with the xenon and ton. It's called Panda X. And finally, a third family, which was the LUX Zeppelin, 2 communities that are together, which also was coming, it was a spin-off from the xenon community. So it's a community growing and splitting up, as if all of you were going around after your PhD in the world and start the same experimental effort. So now we have a large community of people working on the xenon experiment, unfortunately competing until now, because then I very recently started to join together again in the XLZD consortium that unites the LZ community with the xenon and ton community into a joint, a common program for the future to go to a detector which will be of the order of 40 to 60 tons of xenon, and which will be called either Darwin or XLZD or maybe another name, I don't know. Parenthesis. Darwin was originally thought as the experiment that would gather the community. And when we were at the scale of 100 kilos, we thought that this community of the noble liquids should really unify in order to reach these large size detectors. And that was done by unifying argon and xenon community. So Darwin was originally a project to have both argon and xenon detectors running together and exploit the complementarity of the two targets. Then the two communities split again, and now we are competing again. Okay. So another thing that I show here are the highlights, to my view, of the results obtained with this kind of detectors. So here you see the level of the background, electron recoil background, going from the first generation experiment, and here it is represented by Panda X14, okay, down through xenon 1 ton to xenon n ton, very, very low levels of electron recoils. This means that we have really controlled the background coming from radon and other beta decaying nuclide in xenon and ton. So this is a really impressive results from xenon. On the other hand, as you see, the discrimination power between nuclear recoils and electron recoils is the limit of this kind of experiment. Here you see the final result of the xenon and ton, where the latest results, let's say, where the many candidates in the region of the nuclear recoils, for each of there are many candidates, and for each of them you have to evaluate the likelihood that they are coming from either background or a signal from the wind. So you are already dealing with a non-zero background experiment in this case. On the other hand, the nice thing about probability is that you can have under fluctuations, and so the most recent result of the LZ community published, actually not yet published, but presented at the summer conferences, under fluctuated down to a very, very low level of the cross section, and in this gained space over the competitors, which are quite above LZ. But this is just a statistical fluctuations. They're more or less the same sensitivity. So here are photos of these big TPCs. This is LZ, this is xenon and ton, and this is Panda X. And you see that we are now at the level of 10 tons. In all cases, you have an array of photomultipliers on the anodic, above the anode, and an array of photomultipliers below the anode. These photomultipliers are more or less all the same, because they need to use this cryogenic photocathode that I was mentioning this morning. They all have to use krypton and radon removal techniques, which I was also mentioning, and I will show you. I think I have a picture of these plants that are needed in order to have these experiments running. And in addition, they all have veto detectors all around them, which use standard technologies, so either water or liquid scintillators. And in case you want to use water in order to detect the neutrons and either neutrons coming from the local radioactivity or from spallation from muons, it is good to dope this water with neutron sensitive material like gadolinium. And this is done, for instance, for the xenon experiments. Then they all use external and internal calibration sources to perform the calibrations that, as I showed you this morning. And the status is that, as you have seen, they compete to go very down in the cross-section, but they already hit the neutrino floor. And in fact, in particular on the solar neutrino part, they had very recently the first detection of boron-8 neutrinos coming from the sun and coherently interacting with the nuclei of the detector. So this is a nice summary of the present measurement from Panda X and Xenon and TON, which was compiled by Roberta Calabrese, where you can see that in addition to the very precise measurement that you can have with solar neutrino experiments, which detect substantially the interactions on electrons, for the first time, these experiments that detect interactions on the nuclei, coherent interactions on the nuclei with very low energy, can measure the boron-8 neutrinos, not with large precision at the moment, but you can foresee that in the next future this precision will increase. So this demonstrates the capabilities of these experiments as solar neutrino observatories. Once you go to larger masses and larger exposures, you will have larger numbers and can use these experiments also as solar neutrino observatories. So these are the proposals for the future. The detector concept is identical to the current detector, so there is more or less no striking innovation. There are problems, there are challenges that you have to address in order to scale up the technologies that are being used. But the basic technologies are going to be the same. So, for instance, for the Darwin experiment, which is envisaged to have a total mass of 15 tons and an active target after visualization of 40 tons, you should use around 2,000 3-inch photomultiplier. That's the numbers that you should use. And you can use gadolinium doped water as in the xenon detector in order to detect neutrons. XLZD is practically the same things. And Panda X will have more than 30 tons at Jinping, which is very low. So they have an advantage being very low in a very deep underground laboratory. But again, smaller PMTs, but more or less the same thing. And they will reach 10 to the minus 49 square centimeters sensitivity in the cross sections. And as I said, will be limited statistically by the neutrino floor. So what are the challenges to scale up? The challenges are, first of all, connected. We were joking this morning about the high voltage, but already at the current size of the xenon and TON experiment, there have been problems and obliging the collaboration to go to low voltage, low fields, and so low velocities, which for a large detector would be a big problem because you would have piled up signals S1 and then signals S2, difficult to prepare one another because you have too many events developing slowly in the detector. So to reach the size, which is not so much larger, but it is larger, 2.6 meters, you have to work on the electrodes and on the feed-throughs and on the way you set up the electric field in the detector. This means, you see here, for all the TPCs, you have elements, electrical elements all around the volume, which are needed in order to have a uniform electric field inside the detector. And of course, you have many resistors. There is a divider which provides the different voltages to many different electrodes in the detector. So one problem is this one that is being addressed with research and development. I was speaking to Marco and he was just telling me that they are setting up small TPC in order to test new technologies for these electrodes. Then there is a problem to control the liquid level on such a large detector. There is a problem in pushing beyond the current limits the purification for radon and krypton below the solar neutrino level. And finally, to get to a very high electron lifetime above the 10 milliseconds level. So these are the topics for R&D, and this community is really prolific in projects for R&D and also in WIN ERC projects. I must say there are 3. big ERCs on these activities. One is this Xenoscope, which is a small but very long detector installed, I think, in Zurich. Is it in Zurich? Yes. In order to develop technologies for this long drift. There is a small but large demonstrator called Pancake in Fribourg, I think, to study the technologies connected to this large width. And then there is a third one, which is no picture here, in Münster, to develop the purification techniques for radon, I think, by Christian Weinmann, no? Yes. So 3 ERC projects on this. Take the chance to submit yours. Let's go to argon. Similar slide for argon. The time scale is more or less the same. The development was a little bit slower. And actually, we don't have so many experiments that were run. We actually had an experiment which I should add here, was called WARP, of the scale of 10 kilos, but then we scaled to dark side 50, which was really the first demonstrator of this technology for dark matter working. And then from there is a big jump to the ton scale. So there are not the many intermediate steps that the xenon community was capable of doing, with the exception of a big, very big single phase detector, which is the DEEP 3600, which means 3.6 tons. So from 50 kilos to 3.6 tons, but not in the tip C4, in the single phase detector. The achievements with argon were essentially connected to the pulse shape discrimination. So here is the plot which I showed you this morning, where I showed you the calibration events with electron recoils and nuclear recoils, nuclear recoils and electron recoils. Here is the results for a WIMP search. And here is the background coming from argon 39 in the detector. And that is the region where a signal from WIMP would appear. And you see the separation is impressive, and that's due to that factor 10 to the 8 discrimination power. So that is the actual result of dark side 50. So here we are in a zero background situation, not like in xenon, where you have a statistical search. This is the discrimination power as measured by DEEP, and this was the thing I was stressing a little bit earlier. That is, dark side demonstrated the very large capabilities to lower the threshold. And in fact, below the 3 GeV mass scale, it set the best limits also against other technologies in the cross-section. Why? Because of a technology which was actually developed by the xenon community, but then used profitably also by the argon community, that is that of abandoning the scintillation signal. Just look for the electron signal. It's anyway a signal. And there, as I told you many times, you can extract the single electron. So you can go very low with the threshold. While when you look for photons, in particular with argon, where you want discrimination capabilities, you have higher thresholds. So here you have a very, very low threshold that you can reach with the so-called S2 only signal, so only charge. This is an image of what will be the next step of the dark side family, which is dark side 20K. I will spend a little more words because it's my experiment on this. What you see here is a cryostat that you will also see later when I will show you the neutrino experiment. In fact, it's identical to the protodune cryostat, which you might have seen at CERN. And it is a breakthrough technology that allowed the argon community to go to the 100 tons and 1,000 ton scale. At that point, you cannot use the standard cryostats which we use, which are vacuum vessels. Okay, you cannot do such a large vacuum vessel. And this technology uses instead the same technology used by natural gas ships, those that transport the natural gas over the sea, and it allowed to go to thousands of tons of argon inside. Inside this large cryostat, so you have argon as a bath
thermal bath, and then the standard TPC. So also here you have a chissà che numero è. Also here the community joined all together, they gathered. So the community from DEEP, from that site 50, and from ARDM, which is another ton scale TPC that was built for use at Canfranc. They joined together in 2017, I think, so a little bit earlier than the Xenon community, forming the Global Argon Dark Matter Collaboration, which is now building the Site 20K. And they also have a plan to go to larger masses. So let me tell you something about the ranking experiment. So this is DEEP. It's not a TPC, it's a single phase detector, and it's I will highlight the key technologies that were invented and are now used for the future experiments, okay? So here the key technology of this community, which came from the SNOW experiment, you have heard about it yesterday with Marco Pallavicini, was an acrylic sphere. So the container for the liquid argon is acrylic. It's transparent. You can put photomultipliers far away from the inner core, so you reduce the background coming from photomultipliers. Photomultipliers were, for this kind of experiment, the major source of background. There's no cryostat, and the major source is photomultiplier. So you want to put them far away. You use light guides, and you look through these photomultipliers to the inner region, which is contained in this acrylic vessel sphere. Unfortunately, there is a hole, which is needed for the cryogenics, and this is where the background comes from, unfortunately. So the DEEP experiment had a first result, but then they had to upgrade the detector to deal with this background. Alpha particles are taking this road to go into the detector and spoiling their capability of being zero background. So now the experiment just underwent the upgrade and is going to take data again. The TPCs are much smaller. We had a 1 ton scale TPC at Canfranc, as I said, but it never worked very well, so didn't give physics results.
Okay, good question. You said it's not a large, it's a single phase detector, it's not a large TPC. The large TPC is it can be a single phase detector.
It's a good correction. You can have a single phase.
It was not my.
I am biased for dark matter detectors, but you are right. You can have, of course, single phase detectors, which are TPCs.
Okay.
That's it, simply right. I am used to a slang in dark matter. You either have double phase TPCs or single phase non-TPCs. That's why I simplify, but you are right. This is, as I said this morning, simpler because you don't need heat-rules, high voltage. You can go to large mass without all the problems that we are fighting with at the 7 ton scale with xenon. Here you have no problem on this, but still there are other problems because large mass is difficult. The DATSAT 50 detector from which I already showed you results was a TPC 50 kilos with photomultipliers, so very similar to xenon, inside a liquid scintillator Vito, doped with boron. And boron has a high cross-section for neutron detector. So this was one of the key features, innovative key features of DATSAT 50 that was then used by the following experiments. In this case, now we are using gadolinium in the water. But the idea of doping with something which is highly sensitive to neutrons was first exploited here. The main result that I want to show you from that DATSAT 50 is the capability of finding the demonstration, that we could find a source of argon which was depleted in argon 39, the isotope that contaminates the argon coming from the atmosphere with beta decays. So this here is the spectrum of all the recoils observed in DATSAT 50 in a first run that we had with atmospheric argon. And you clearly see, those of you who are experts will recognize a beta decay spectrum here. That's the beta decay from argon. And then all the remaining components from all the other contaminants at high energy. Okay, when then we emptied the TPC from the atmospheric argon and we filled it with underground argon extracted from underground sources, we observed this reduction in the spectrum, which is clearly see here. It's a reduction in a factor more than 1,000, reaching levels of 0.7 millibecquerel of argon in the underground argon. So this was the breakthrough because it demonstrated that you could do large-size argon detectors with reduced contamination from argon-39. And so we had to develop a full industrial program in order to extract this argon for the next generation experiments, which would be the X20K in this case. So we extract the argon from the same source from which we extracted the argon for Duckside 50, which is in Colorado. Why do they have argon sources in Colorado? They don't. So they have CO2 sources in Colorado. Actually, they have reservoir, national reservoir of CO2 from underground sources. Do you know why they use CO2? No. Just imagine, you want to reduce the amount of CO2 in the atmosphere, but you take it from underground to do mineral water. No. Good idea, but it's not that. The idea is that they want to extract oil in Texas. So in order to extract oil, you just make a hole and the oil comes out. But when it's going to empty, you have no pressure, so you fill it with CO2 and the oil comes out from the bottom. So they use CO2 for the Texas wells of oil. And we went into the place where this CO2 is extracted from underground and then sent to Texas. And we put there our plant that takes from this CO2 a very small contamination of argon that is present in the CO2. And then we refill the CO2 in the pipe for the Texas plants. Okay, so then this argon is shipped through by sea to Sardinia, where we have a purification column, which you see here. It's the highest column in the world, is as high as the Tour Eiffel. And so they would never allow us to build such a huge thing on the ground. So we went and looked for a mine, so for an existing hole of 350 meters, and put the column inside the hole. And then from there, the argon is sampled and sent to Canfranc, where the ARDM experiment is now used as a veto detector for the DART small detector, which samples the argon 39 inside the underground dam. And finally, it arrives to LNGS to fill the Darkside 20K experiment. I already told you about this structure. Now I will tell you a couple of words about the TPC, just focusing on the innovations of this TPC. So the first innovation is that it doesn't use photomultipliers. I told you that it was really a pain to use these photomultipliers in argon, so we abandoned and we developed our own photosensors based on silicon PLs. So solid state technology, radio pure, and working at low temperature with very high efficiency. So here you have 20 square meters of silicon photomultipliers on the top and on the bottom. Second innovation is that the electrodes are transparent. They are made of acrylic. For this, we use the knowledge coming from DEEP. And all the TPC actually is made of acrylic panels. And we use the TPC itself, the walls, as a veto. So this is another smart idea. This is how the panels of the TPC are built. And you see that you have PMMA, acrylic, inside at the middle, and then you have a thin layer of underground argon. On one side you have the TPC, and on the other side you put another thin layer or radio pure argon, and then neutrons will undergo capture on hydrogen and emit photons at 2 MeV, which is a normal process of neutron capture in hydrogen. And these photons will be seen with high efficiency by photosensors which are placed in the external argon. So you use the wall of the TPC with that criterion of having doped the object with something that has high cross-section for neutrons. This is a smart idea. The silicon photosensors, as I said, you have to cover around 20 square meters of these photosensors. But silicon PMs are normally of the size of 1 square centimeter. So you are talking of 100,000 channels, without channels. You could not do that. What we did, not only we developed the silicon photomultipliers themselves in order to have them work at low temperature, but we also developed the electronics in order to assemble large photosensors. So you first assemble single silicon PMs into a tile of the order of 10 times 10 square centimeters, and then 16 tiles, sorry, this is a tile, and then 16 tiles into what we call a photon detection unit, which includes 16 tiles and is 20 by 20 centimeters. So this big object requires cryogenic electronics, which we developed, and you see that the performances are very good. You have a much better resolution with silicon PMs than with photomultipliers. And also we had to build very large facilities, both in Gran Sasso laboratory on surface, where we assemble this PDU, and in Naples, in my laboratory, where we test these PDUs. Okay, this is a advertisement. This is my baby, a Proton Zero TPC, a small dark side 20K, more like this. Detector, including all the innovations I've mentioned, acrylic, transparent electrodes, and silicon PMs and electronics, and running in Naples in order to vet all the new technologies. This is a 1 ton mock-up, as we call it, that is being installed this year in Gran Sasso laboratory. Okay, so the capabilities of dark side 20K are similar to those that I showed you for the xenon experiments. They reach 10 to the minus 49 square centimeters, and in addition, they will be sensitive down to the neutrino floor, also in the low mass region, down to 1 GeV, more or less. Okay, what time?
We have 40 minutes.
Please.
Which is the time here for that type of here?
What a nice question. So it's going to run in 2022. 2 years ago, and we are late. So I could say that the time scale is 2026, but who knows? We are trying hard. It's very difficult. Yes.
And why do you have two sensitivity limits for that side and one with?
The question I hate. So normally you will find on our let's say no, this is not for this reason, fortunately, because in our previous paper we had two curves, the one which I showed you before.
Yes.
But you were not asking for this here.
They are not the same.
You see two lines?
Yes.
So I will not answer because you didn't ask. I will answer here. Okay. Here, fortunately, the answer is easier. One is with a threshold at 4 electrons, and the other one is with a threshold at 2 electrons. And maybe I should have stressed, just a moment, I should have stressed that this is in only 1 year of time. So this is easy to reach. Yes.
I have two questions. First one is, suppose you didn't have the low temperature issues with PhDs, would there still be benefits? Do you think the benefits?
I didn't get it. I'm almost sure.
Suppose you didn't have the low energy issues with the PhDs, would you still want to use the silicon methods? Are there any other benefits?
The issues with the PMPs, you're asking.
As in, is it only to get over low energy use?
No. The PMPs work bad enough. If you want my idea, my impression, I've been working with them for 20 years, they don't work. So forget about using photomultipliers. Because it's very low temperature and you need very much care to use them. So nothing to do with the sensitivity at low energy. Of course, they are also a rich source of background. This means that if we were using PPPs, which we are not for other reasons, that would be the major source of background at low maximum, and you're right. In this case, silicon is not radioactive, it's very radio pure, but all the remaining components, in particular the cryostat, vessel, are radioactive, and that's a limit alone. That way you, hello, Max, sorry.
Second question, on the boron 8 stuff,
Yeah.
you said that it was something like 2.6 sigma. Is that enough to claim discovery?
I would ask Marco to answer.
Yeah, indeed, we didn't claim a discovery. It's reported as a measurement or in the title of the TRL as an indication. The difference is that here we are not claiming for a new physics evidence of something. It's a confirmation. Neutrinos are there, coherent scattering is there. It's the first time that we can see them in a dark matter experiment. So we are scratching the head of the neutrino floor. This is the point.
You have a fantastic group working on social media. And no, it's a great achievement, and there was also a race, no, between the different experiments to state who was first in observing them. And these are very, very precise experiments. They are doing astonishing things in understanding what they see in the detector. Okay, so neutrino physics. I won't go through this slide because you had 4 hours of what are the main questions in neutrino physics. The only thing I want to say is that Nobel liquids will try. Nobel liquids are being used trying to address all these questions, let's say. That's all they will answer. So, I think you already saw an example of neutrino event reconstructed in a Nobel liquid TPC, in particular liquid argon TPC. In this case, it is one of the first large-scale experiments that has been running for many years at Fermi. I already explained the technology. Maybe I didn't stress the fact that in a TPC, a liquid argon TPC, you need a T0. So even before you want to use the scintillation signal in addition to the charge signal in order to improve the calorimetric reconstruction of the event, the measurement of the energy, according to what I explained this morning, even before that you need the scintillation light in order to trigger your acquisition. You need to know where the events start in order to use the drift coordinate to spatially reconstruct the event and have this good quality imaging. So that's why you need both light detection and charge detection. And as I said, the calorimetric properties and imaging properties have already been developed over 30 years and demonstrated in quite a large number of detectors. Icarus, Microboom, Lariat, Argon Cube, SBND, and Protodune are all either head-run or are-run, and are all at the 100-ton scale, so much larger than the detectors that I showed you for the dark matter. But there are also other kinds of single-phase TPC used for neutrino physics. In particular, here I mentioned 2 examples, one single phase and the other one double phase. The single phase, which is shown here, is a TPC which is optimized for energy resolution. So it has the same concept as the standard neutrino TPC with a cathode at the center and 2 wire grids at the 2 sides in order as anodes. But behind these grids, you have high efficiency photosensors with a much larger coverage, photocathodic coverage than what you do in standard neutrino experiments in order to improve the energy resolution, as I said this morning. And this is the EXO detector, which is so much interested in the resolution because they want to study the neutrino is the double beta decay. This here instead is a possible use of a double phase technology for neutrino imaging. In this case, you want to use technologies on the anodic plane that allow you for a large scale detector. So one idea was to have not the conversion to light of the electrons, but the amplification of electrons. So you reach the boundary between liquid and gas, and then you extract the electrons and you amplify them. How do you amplify electrons? You use large electron multipliers. So high voltage applied to resistive plates with the holes in between where high electric field is created in the holes, and the electrons passing by produce a multiplication, avalanche multiplication. Very difficult to control because you have to control the pressure and stability of these objects with high fields, and actually it never worked. So it's not being used in this way, but it's being used, and maybe I failed to show in the slides, in another way. When the electrons pass through the holes, they also produce light, of course, and you can use cameras on the top to observe the light of the electrons passing through the holes, and you can do an imaging. And I'm really sorry that I just forgot to insert this because it's impressive what kind of high resolution imaging you can obtain with standard cameras, CCDs, looking from far away at the top of this gas phase. So this is the Ariadne experiment, if you want to go deeper into it. Okay, so these experiments are being used for short baseline neutrino physics, long baseline neutrino physics, and in general for underground neutrino physics and proton decay. And I will show you now an overview of what's going on that subject. I think I don't have enough time, so 30 minutes? 30 minutes. So it's just a fast overview. The initial TPCs, large-scale TPC, were more or less all the same. A vertical cathode with anodes on both sides and horizontal drift of the electrons. Okay, and this was due to the necessity of limiting the size of the drift to a few meters because of the problem of purity and electron attachment. This geometry was originally used by Icarus, then also by Microboon, and finally it is being used today by SPND, the short baseline neutrino detector, looking at very short distance from the source for sterile neutrinos and neutrino oscillations. The photosensors are not only photomultipliers, but newly developed photosensors, which you might have heard about. They're called Arapuca, with a Brazilian word which means trap. The light coming, the ultraviolet light coming from argon is being trapped and wavelength shifted inside a closed volume, where then through multiple reflection is then guided to a small silicon PR. So that's a way to have a very large sensitive area and very small active area. Of course, the efficiency will be very small, 3% is a standard efficiency, detection efficiency, to be compared with the 30–40% efficiency that we have in dark side with silicon PMs all over the surface. Nevertheless, it was very much innovative. It was even, it won a prize. And it's being used for the Dune large detector. So maybe when you have lessons on the photosensors, you can ask more details about this. Then these big detectors were used to demonstrate that you could have larger drift. So for the far detector of the Dune, I think that this was already shown, no? Dune has got a near detector at Fermilab, and then several far detectors 1,300 kilometers away, deep underground. So these detectors will be both the far detectors for the neutrino oscillations, but also observatories for neutrinos coming from outside. And yes, and for the far detector, two 17 kiloton TPCs of liquid argon are being built now, and two additional modules will be built in the so-called phase 2 of the experiment, which will start after the construction of these is completed. In total, you will have 70 kilotons of liquid argon, unless some other technology is selected for these additional modules. And the two modules being constructed now are one have a vertical drift, an horizontal drift, and the other one will have a vertical drift. So It's 12 meters high, this detector. This means that the drift here is 6 meters, while here is limited to 3 meters. So it was the fact that high purity was achieved that allowed for this improvement and simplification of the experiment to be taken. There are other technological improvements in this detector here. In fact, instead of wires, in the horizontal drift, you use wires for the charge collection. Here you use perforated PCBs, so much cheaper and also more pixelated to measure the charge. And also the Arapuca were made much larger. They are called mega cell because they are much larger than the Arapuca used in the horizontal drift. So the fact that the technologies have been proven in the first module being prototyped allowed for these technologies to be adopted in the second module. And there are many, and these technologies were tested in the ProtoDune experiments. It is also advertisement. Two fantastic detectors in cryostats identical to the X20K, 770 tons of liquid argon each, one horizontal drift and the other one vertical drift, not working together because the argon is only 770 tons. So first you run the horizontal drift, then you take the argon, you move it into the vertical drift, and you run the vertical drift. And that's because CERN finds liquid argon too expensive. Okay, and this is the performance with neutrinos of the ProtoDune. But we also have the NIR detector, which is based on argon, because the necessity to compare the flux measured at the NIR detector with the one at the FAR detector obliges you to use the same target in at least one of the detectors. So we have a NIR detector liquid argon just in front of the beam, and in addition to other two detectors which are measuring in detail the beam with other technologies. And I wanted to stress that this one is again a liquid argon TPC, but it's different because at the NIR detector you have a very high rate of interactions from the neutrino beam, which is very much intense. And so you have a strong problem of pile-up. In order to cope with this pile-up, you reduce the drift to 50 centimeters so that you have several chambers. It's a modular structure with several drift chambers, each separated from one another. And the readout is done with pixelated solid state sensors. So you have a real 3D reconstruction because you have XY determined by the position of the pixel that is being fired. It is a major improvement, in my opinion, in the readout of these large detectors. And I think that any future detector will use this kind of readout. There are several developments for the phase 2. Okay, there will be an upgrade in the beam. There will be the 2 additional FAR detector, and there will be also a new detector in the near position. I will skip this, it's not very important. I wanted to show this one, which is the new technologies that are being explored at the moment for the phase 2 detector. I didn't mention on the slides, but I am leading a newly formed collaboration, which is called the DRD2, Detector R&D at CERN, focusing on liquid detectors, in particular with noble liquids, and many of these R&D are being developed by this collaboration. So I wanted to show you. So one possible development is to have on the same sensor the readout of both charge and light, and it's obvious. Why having this problem of the transparency of the electrodes in order to read out the light, in order to increase the surface? Once you pass to solid state photosensors, you can have on the same chip sensors optimized for the charge and sensors optimized for the light. Silicon PMs and pads, essentially. And that's the solar development. Here, this development is just pixels, you see, so a number of these will measure charge and another number will measure light. So on the same surface, you can measure both charge and light. And this is, of course, scalable. Another set of developments aims at lowering the threshold in these detectors in order to do solar neutrino physics and dark matter physics. Why not dark matter physics in such huge liquid atom detectors? So here you see the signals that you obtain from supernova neutrinos, 10 MeV scale, from boronate neutrinos, 10 MeV scale, from xenon decay. If you dope the argon with xenon, you can do xenon neutrinoless double beta decay inside the huge liquid argon detector at MeV scale. And then if you go even lower, you have a problem coming from argon 39, but if you use underground argon, you can go to dark matter physics. This is the Ariadne, which I already described. New ideas for the future phase 2 detectors in Dune. And this is another idea to detect charge and light. You simply coat your charge pixels with a photosensitive material. The photosensitive material produces electrons that are measured by the charge, because charge and light are produced, but they arrive to the sensors at different times because the charge has got to drift. So you first get S1 from light on the same sensor, and then you get the S2 without double phase, let's say, from charge after the drift. I think it's fantastic richness of developments that are being studied for the future of humans. Okay, so if you go to even lower energy, then this slow-mo is an idea which is at the moment pure fantasy, but why not? You can put acrylic in a small part of the big 17 kiloton module and use a small dark side with underground argon to do in 1 kiloton, for instance, out of 17, direct dark matter searches. Just put silicon photomultipliers everywhere and use the acrylic for vetoing the ground. You have a radio pure volume inside a less radio pure volume. And then, as I said, if you dope, heavily dope with xenon, then you can even reach the normal hierarchy for the neutrinoless double beta decay because you have huge quantities. Questions?
On Dune and maybe also dark side. So the light that goes into the PMMA and does not hit the silicon photomultiplier, it's just lost, right? It's not reflected back into the detector, or is it?
Okay, this is a nice question, and I can answer, but this is just a sketch. Okay.
Okay, so
I can answer. I would put reflectors all around. You need anyway wavelength shifter, and what we use in this case is layers, not evaporation, because you cannot evaporate such huge, but layers of very thin micrometric, nanometric materials which are transparent, but they emit light in the visible region, like pen. This has been tried. Of course, you lose quite a bit of light, but you can use the sensors which are outside to recover part of this light. All the part of light which is re-emitted inside will be seen by the photosensors. Okay, but that's my idea on how to solve this. This is very far from being demonstrated, let's say. And it's an idea for you to think in the next 15 years. Okay, that's the time scale of the phase 2. Yes.
The pixelated sensor you show in the slide before, the one with charge and light.
Yes. This one.
No,
This one.
Yeah. Are you going to have an advantage on the collection, or you are going to lose light when it goes in the charge part?
No, you will never have full coverage of such huge surfaces. You are talking about thousands of square meters in a single Dune model.
Okay,
so there is a fraction. You would put sensors on a fraction of the surface, and that fraction is organized in that way. Okay. Yes, and then you can have also multiplexing because you cannot read out every single part. And this is still in the R&D phase, but I personally think that this is much more innovative. Here you put a layer of paint on your charge detector, and that layer emits charge when it is hit by photons. Fantastic. Okay. Last topic, which I thought I would never manage to cover.
15 minutes.
No, even too much, because I don't have many details. It's how to use these technologies for the neutrino double beta decay searches. Okay, you already heard about the physics. You need to have a very high energy resolution to detect the possible appearance or excess of events on the tail of your spectrum of double beta already rare events that are occurring in your detector. And the requirements are large masses. Okay, high isotopic abundance, but this is a doping that you have to do of your SIM. Ultra low background noise and good energy resolution. So apart from the energy range that we are talking about, these are similar requirements to the dark matter experiments and also similar to the future Dune experiments where, as I said, the main focus is to lower the energy threshold to really do solar neutrino physics, so in MLB scale, you know? So challenges are very common. And as a consequence, also the solutions that are being proposed are very similar. So this is a slide just to show you, as I did for the dark matter experiments, that there are competing technologies. It's not only noble liquids. In this case, I think personally that the most dangerous is the legend community, which at the moment, which did a great job with the Gerda experiment and will surely do a great job also with the legend, now legend 200 and later legend 1000. So these are using germanium, but they are also using a noble liquid argon to cool down the germanium and as a veto. So they are also using the technologies that we have been developing for that matter. Low background, photosensors, and so on. Possibility of xenon doping. Then there is a possibility to do it only with scintillation, like in Camlan Zen or in Snow Plus. And finally, there are the bolometers like Core, which is already leading and the future in this case is scintillating bolometers like QP. But we will focus on the noble liquid TPCs, which I already showed. So now I give you a little bit more details. First of all, the experiment is 175 kilos of liquid argon, 80% enriched with the double beta decaying isotope xenon 136. It is it took data until 2018 at WIP, and it had a veto and a shield around, like for a dark matter experiment, you have to reduce the background coming from outside. As I said, the key feature of this experiment was the large photocathodic coverage. And here, they were not using silicon PMs, but they were using the so-called large area avalanche photodiode, which is something similar to the silicon PM. It's not run in Geiger mode, I think. It's run in a proportional mode, so not exactly the same, but the idea is to use a solid state detector, which will reduce the background and improve the resolution. Photomultipliers are not the best in terms of single photoelectron resolution. These are pictures of this detector that ran until 2018, and the new experiment will be the Nexo experiment. I actually don't know whether it is approved. They are pushing a lot in order to go to SnowLab, and SnowLab would be happy to host them, while Legend would go to Gran Sasso Laboratory, and also BID. So that's more or less geographically the distribution of the future experiments. But I don't know if they have been funded. I don't think so yet. I hope they will. It will be a larger size, so you will have a similar TPC, let's say, but they will abandon the central cathode and have a single cathode and a single anode. For a total length which is around, I think, 1.5 meters, the size of this object. And also they abandoned the large avalanche photomultipliers. They've been developing and studying silicon photomultipliers, which will be put in the bar. So all around the detector. This is a new feature. You have not seen any other PPC with this silicon PMs on board, so this is something new. So they have quite a large 4.6 square meters of silicon PMs to be developed, and they are very active in the development of these new photosensors. They will be read out with a higher granularity with respect to dark side. I told you that dark side will have 20 square meters of silicon PMs, but the readout channels will only be around 1,000. So because they are ganged together, they are multiplexing. Then they use an external water Vito detector and a vacuum vessel in order to keep the TPC cold, together with this hydrofluoroether thermal bath that will also act as a radiation shield. So I think that this is all I had. I missed a lot of topics. For instance, I didn't speak at all of the experiments that have been developed with noble liquid, in particular with argon, for the study of the coherent neutrino interaction. They are smaller experiments on the other hand, and so they are also, my point of view, a little bit less challenging with respect to what I have been showing. And I didn't show you anything about what is being done with either with argon or with helium at the level of the R&D. For instance, there is the development of a scintillating bubble chamber done with argon kept in a quasi-stable situation, so that bubbles are originated when a nuclear interaction occurs and are not originated when an electron interaction occurs. This means abating with the ground, but it also circulates. And many other developments that I have not covered because they are really at the level of the R&D. On the other hand, this is the interesting thing for you, because it's an ever-growing community and where many ideas, new ideas are welcome, so you would be welcome to join if you are not already. If you are not already, join this community and produce, because this is a line of development that will last at least for the next 20 years, both for that matter and for neutrino technologies. Thank you.
Giuliana, really very nice and helpful overview also on the neutrino sector. So we have time for a few questions. Maybe you have also some of them for the first part. Please tell me.
So with the silicon PMs at room temperature, they do have a very high dark hole rate. Is that like liquid xenon still? Is just the temperature going down to the liquid argon temperature enough to kind of mitigate that, or is there something more you're doing? So you can.
Thank you for this question. This is my field of research since many years. So yes, you're right. The low temperature helps a lot because the counts in silicon PMs at room temperature are essentially due to thermal agitation. So it's obvious, and it was obvious already in 2007, that going to lower temperature, these problems would be dealt with. What was less obvious is that the mechanics, let's say, the design of the silicon PMs and very basic conceptual design would not be immediately applicable to low temperature. In particular, you know that the Geiger discharge in the silicon PMs needs to be quenched. And this is done through a simple resistor, the quenching resistor.
So you just put in series a resistor with the diode, let's say. And when the current starts, then the voltage drops across the resistor and quenches the shadow. But that resistor was made polysilicon, essentially, together with was grown together with silicon. And so its resistivity would increase a lot at low temperature, and so the value of the resistor would change, and the device would not work anymore. So for a long period, we had devices that did not work. Either they worked at low temperature or they worked at room temperature. Now these resistors are made in metal, and this problem is solved, and you can work both at high temperature and low temperature. So you can study the behavior of these dark counts, and you can disentangle the different components of the dark count, and of course you completely reduce, if not at the xenon temperature, at the argon temperature, you completely remove the thermal noise. You are left with other components of the noise due to crosstalk between the different cells. So there was a long R&D in order to reduce this component via trenches. Now all the silicon PMs adopt these trenches, but then you have anyway impurities generating after passes. And so there are other components that still give you a dark count rate at low temperature, which at the argon temperature is of the level of millihertz per square centimeters, per square millimeter. So it's really very, very low. I must say, but only if the registration is off, recording is off. Can I put stuff? Pause.
Why, when you show the recent LZ results, you said it was a statistical fluctuation, but all the other detectors have seen under fluctuations as well, so lower background, so they've all benefited from it.
Yes, you're right. I'm not an expert of the statistical analysis of this experiment, but you might see, a minute, I show you, that there is a band. The actual result of the experiment is shown with a band, a colored band. And the actual limit is within this band, but the band shows you the statistical range that can be investigated by the experiment. So you see that this limit is at the lowest boundary of this. That's why it's an under fluctuation. It should come more or less at the middle, no? If you evaluate the sensitivity, then you will have the central value, the 1 sigma region, the 2 sigma region. And then the actual limit can happen in this band, and it happened just at the lower boundary. I want to show you.
I think this question is the perfect bridge to the next, which aims to cover both.
Exactly.
Here it is.
Well, I can't be partisan about this anymore.
So you see, that would be the average limit that you would obtain doing several times the same experiment. And this time that you did it, you obtained this limit, which is at the lowest part of the band. You were lucky. Actually, xenon was unlucky in the previous experiment, no?
In one part of the band, yes. It's multi-canals that way.
Yeah, we'll get to the details, but I think it's important to say, if everything is correct, Alzette was lucky. Because you can also see these if you're really unlucky.
Yes, actually, I think that the xenon experiment in the previous, after the first year of run, we were all eagerly awaiting the results, and they were not so good, no?
So there was an
Overfluctuation
with respect to the
Yeah.
expected background.
But also to give Alzette a fair shaking, that for this result, their sensitivity is much better, right? By now, they have unquestionably the best sensitivity. For the last round, sensitivities were similarly no.
All day.
Alzette now has the best.
No, I joke because I am doing a talk, not at a conference, not from the collaboration, and it's not even a review talk. I am talking to students, so I have to say these 3 experiments are very similar sensitivities. Okay, There are three very good communities that demonstrated several times to know what they're doing, control the backgrounds, extract good results. And depending on the month, or even sometimes on the day on which you look at the archive, you see that the leading experiment is LZ or Xenonenton or Chandelier. So it occurred to me that I gave a review talk on the 28th of August, I don't remember. And I only found the result from Panda X, and the same slide showed the results from Panda X. And then after 1 month, I discovered that there was this result already on the internet, but I just missed it for 2 days. And so it was not up to date, my review, because they are really running one after the other. And it's a good thing that there are so many conferences, so they always have the occasion, each of them, to be the leader. That's my opinion.
Any other question? I have one, if you probably can provide a short answer. You mentioned this idea of adding xenon, enriched xenon 136 to argon. But what is the gain? I mean, why would it be better to do in this way with respect to collecting xenon 136 and make a xenon experiment?
I'm not sure if I have the right question, but it's a good question to address because I maybe didn't cover this, which is an area of many large activity. Many people is thinking to this. So why would it be bigger? We should make some math and see a few percent of xenon in 17 kilotons of argon. How much xenon is it? Larger than your experiment, probably. And that's the answer for you. Second, of course, you have to get that percentage.
Okay.
Okay.
Assuming that you have the mass of xenon 136, what's the best choice?
But I think if you have,
Running argon or running it alone? This is my question.
so, I don't know, here you already have this large detector and you only have to do it with xenon and you obtain everything. In addition, and that's what I wanted to say, we are in the argon community more or less everywhere, from the double beta to the neutrino and even in the dark matter, thinking to do argon with xenon. Because it's a good way to wavelength shift without using wavelength shifter, so losing any, okay, with TPB you don't lose any, actually you increase the amount of light, but TPB is really difficult to put on 1,000 square meters of surfaces. So pen you reduce the light of 50% at least, so it's not a good idea. Xenon would allow you to recover all the light, because all the light is immediately, the excited argon immediately transfers these excitations of the energy to the xenon. And then the xenon produces the signal. So the signal is produced in 175 nanometers as in xenon, so it's much better detectable. Just to make an example, the silicon PMs at this moment have maximum 15–20% efficiency for 128 nanometers, while for xenon this is much improving. They are already working about above 20% PD, photon detection efficiency. Okay, we are trying to develop silicon PMs which are sensitive down to argon, but will never be as sensitive as with xenon because it's difficult. So this would be better. There are also other things that would be better. For instance, the transparency of argon. I didn't talk about the light attenuation, but that would also improve with the xenon doping. And it has the temperature is same because it will stay. The main amount will be argon. And by chance, Prototype already ran in a xenon doped version. By chance, it was by accident, let's say, not by chance, because there was a loss of light due to nitrogen contamination. Nitrogen is very dangerous with argon, but it seems that when you dope with xenon, you don't care because the quenching mechanism of nitrogen is lower than the quenching mechanism on xenon. So xenon hits the light before you lose it on nitrogen. So all good things. I was very technical. I'm afraid that I cannot go into all these details, but there are many good reasons to dope
argon with xenon. And this has been tested thoroughly, mostly from a thermodynamical point of view, because xenon would freeze in argon. So you have to keep the concentration low and movement around so that you don't have ice of xenon inside the atom. You need to mix it. And so studies, systematical studies are being done as a function of the concentration of the xenon in argon to study this thermodynamics, let's say, issue. And so I cannot say, although there are papers on the subject, that it's really feasible to put percentage of xenon. But if it turns out to be, then with a single detector, you do solar neutrinos, supernova neutrinos. I didn't mention that these do as news, no? Huge detectors, and also the community could gather. I mean, you do everything in one detector, from beta decay to dark matter.
Okay, I think with this, we thank Giuliana again. So now we would like to have the picture right now before the coffee break. So we go in the amphitheater over there. I think we have to go through this door and downstairs, and then we have the coffee break. Okay, so very quickly we move down, picture, and so on. This picture is of course without the t-shirt. Tomorrow morning we have another one with the picture. But since we are don't know how the weather is tomorrow, better to have it one.
Ma io non ce l'ho la t-shirt.
No, no, questa è sempre adesso abbiamo tutte le
And there was a small one. Yeah. Science inglese invece che in italiano.
Un'altra cosa, i nostri risultati bellissimi. Si parla. Si parlava di questo.
Era dimenticare questa? Sì. Domani.
Ok, figata.
The basic thing, basic thing,
Parlava di posso dire che per quello mi ha chiesto cosa sul mezzo cioè si fa proprietà, ma effettivamente ha ragione, per lo il terzo è il processing analysis. Lavorarci infame che esiste. E poi esatto, fare risultati con le online correction e con le online correction. Se non affini nessuna correzione se non di quelle.
Yeah.
Ce n'era una lì nella sala di poster.
Grazie.
Guarda,
Certo.
forse mi sono persa la risposta.
Come si fa?
Segnare.
Una funzione di dark matter e cioè, magari,
È il problema.
ok,
È proprio il problema, nel senso che se ricevi 100 positroni, non puoi sapere se vengono prodotti da una pulsar, se vengono prodotti da una matter o da una qualcosa di tipicamente quello che devi fare è i dati di forme spettrali, cioè capire qualcosa sulle forme spettrali e sulla morfologia del segnale. La morfologia vuol dire la distribuzione spaziale. Le forme spettrali vuol dire tipicamente, però poi sono stati magari tipicamente dalla statistica degli aspetti una cosa per noi positiva. La statistica degli aspetti è una cosa che scende da una pausa, uno spettro che scende da una pausa. Perché rispetti questo, perché non riesci a ottenere delle codici che sono poi possono proprio dentro il cesso, allora arrivano sempre tutto questo. In realtà poi, con per esempio, quando famiglia si è sperimentato saliva così. Allora, discendente, il tutto citare che ok, questo non c'è da quanto, la visione che c'è questo lato. Quello che poi si è anche visto che esistono anche delle risorse che producono anche loro esattamente un bacco. Perché adesso la discussione è proprio, è un eccesso di un banco di trasformato o un banco di una sorgente fisica prima non considerata correttamente? Questo.
le caratteristiche.
Cercare caratteristiche, per esempio la morfologia del segnale, cioè se se guardi verso il esempio e vedi una sorgente graficata che è distribuita allora ti dici, se non riesci a risolvere non riesci a risolverlo, puoi aspettarti che sia relativo alla statistica, che è allineato sul piano dove stai risolvendo. Se invece vedi un'emissione che risulta dire anche al di sopra e al di sopra di un grafico dove non hai stelle, allora quindi utile la morfologia del segnale. Per esempio, ogni singolo caso va portato. Sempre parlando dello spettro, per esempio, il gamma, una cosa tipicamente collegata alla matematica, c'è la gamma line. Se vedi una linea che è precisa di gamma, quella è un segnale che la soluzione della matematica significa che è in gamma. Quello è un altro scempio rispetto a unicamente la soluzione luce produce una dimensione nuovo, con per esempio il fatto che dei dati, una sistematica Una linea la trovo, per marker, qualche soluzione. Proviamo. Just the projection. Sorry, just the projection.
That's clear as it did before. Are you worried it's out of focus?
I don't know, or I'm making new glasses. What?
I think it's fine. It's always a lot.
Cheers. Found an old like introduction to Windows 95 book. All the things, all of it.
So in 5 minutes, they will be here. So that's done. Yes.
Did you have this?
Yes.
Ah, please, yes, that's great.